Good afternoon, everyone. My name is Davide Proman, and it's my pleasure to chair today's webinar of the UK Quantum Fluids Network. So today we're going to have Lauriane Chomaz from Heidelberg University. Let me give you a short introduction about her. So she did a PhD at École Normale Supérieure with Professor Jean Dalibard, and then she stayed to work with Professor Jean Dalibard until 2015, and then she moved to Innsbruck to work in the group of Professor Ferlaino, and until 2021, where she finally moved to Heidelberg University and start building her research group, working mainly, I guess, in dipolar BEC. I think we're going to hear more about that during her talk. So Lauriane is happy to take your question during the talk. In case you want to ask questions, please do unmute yourself. In case you want to type questions in the chat, I will read this question at the end of her webinar when we will start the question session. I should also remind you that this webinar is recorded, and if you can turn off your camera and mute yourself so that we have the best connection possible. All right, so Lauriane, the stage is all yours, and tell us more about exotic many-body states in dipolar quantum Bose gases of magnetic atoms. Thank you.
Thank you. So hi, everyone, and thank you very much, Davide, for the invitation and for the nice introduction. So indeed, my talk will be about ultra-cold magnetic atom and like the physics that we can do with it. And what I would like to do in this talk is, after giving you a short introduction to our platform, to make a sort of review of the work that have been done since roughly when I joined Innsbruck, and the different discovery that we have made in this system related to quantum stabilization and new phases of matter that arise. And then I would like to give you a short overview also on the new platform that I have been setting up in Heidelberg, and like what are the physics that I want to look at here. So yeah, if you want to know more about this platform of magnetic quantum gases, you can have a look to this review that we set up with like many of the main actors in the field, and that was published at the beginning of this year in this reference. So to start my introduction, actually I would like to take a perspective that I hope is speaking to your community, but it's related so to go back to this really fundamental aspect of looking at interparticle interaction in the ultra-cold dilute regime. So in this dilute regime, you know that we can consider only binary interaction between two atoms, and this is represented by interaction potential, VR. And you may also know that if VR is scaling with 1 over r power of n with n larger than 3, then this potential is well approximated by a contact pseudo potential, which I wrote here. And the nice thing about this is that it's all given by a single scalar parameter, which is this S-wave scattering length. And what is really nice also is that it's applied to most of the interaction that we found in ultra-cold quantum gases in general, because the dominant part comes from the van der Waals, which has n equal to 6. And the additional thing is that we can also tune the value of this scattering length parameter via what we call a Feshbach resonance. So just by tuning the value of the magnetic field, we can change at will, in a sense, the value of the scattering length. So this is really simple and really powerful, and it has made a lot of, it is at the basis of a lot of discovery that occur in the field of ultra-cold quantum gases. However, it's also limited in variety, and it's one of the reasons that people have been for a long time looking in different kinds of interaction that can arise also in these ultra-cold gases. And here I will talk about one, which is the dipole-dipole interaction. And I wrote here the formula for this dipole-dipole potential in its full glory. And what you can note is that its scale is as 1/r⁴. In this sense, it's long range, even in the ultracold regime. And the other aspect that is important is that it is anisotropic. And these two components that remain in the ultracold regime raise prospects for new physics, both at the few body and at the many body level. So that's what we are interested in. And there are also different platforms on which we can have this dipolar interaction coming into play. And the one I will be focused on is simply using the magnetic dipole moments of the atom in their current state. So what you see in this periodic table, represented by the color going from blue to red, is the dipolar length that sets the strength of this dipolar potential. And I also highlighted the species that have been Bose condensed. And you can see that there has been a trend starting with chromium, but also going to other species, into looking into atoms that have like a sizable dipolar length and therefore sizable dipolar interaction between the atoms. And in particular, what has been really a game changer is the advent of these lanthanide ultracold gases, starting with dysprosium in 2011 and then erbium in 2012, that have dipolar length that are on the order of 100 Reynolds. And these lanthanide have also other nice property that make them like easy to use in our kinds of experiments. So in this talk, what I would like to focus is to use this dipolar interaction, to use it in a simplified setting where I only consider a polar state, so I set a value of the magnetic field, and what remains of the full dipolar interaction that I showed you is this elastic term, which is again long range and anisotropic depending on the orientation of the dipole compared to the interparticle axis. And I will consider bosons. So I have again another source of interactions, which are the contact interactions, as I presented you before, that come from the van der Waals mostly. And what is remarkable for the lanthanide is that these two types of interaction, the two length scale that represent this interaction, they are actually on the same order at the background level. And the additional interesting point is, as it was the case for alkali atoms, we can also tune the contact parts of the interaction via what we call this Feshbach resonance and changing the magnetic field value. And therefore, we can tune also the competition in really a fine way between this contact and these dipolar interactions. So I had a slide that is maybe a bit more for the specialists, and which is just making a small detour here, is about let's say, this possibility of having Feshbach resonances in lanthanide and the specificity of the case of the lanthanide. So this specificity, it comes from this Feshbach resonance, they arise due to interactions that occur between different channels of the scattering, and these channels, they are just, let's say, representing the internal state of the two colliding atoms plus their relative motions. And the specificity of the lanthanide is that we have a large number of these collision channels due to the large spin. And we have also a strong coupling between the channels due to the anisotropy of the interactions. Therefore, what arises here is really a dense forest of Feshbach resonance. So here what you see is after loss spectroscopy. So just looking at the atoms that are lost at a given value of the magnetic field set after holding the atom for a certain time at this magnetic field, and each of the spikes correspond to Feshbach resonance. So we have really a lot of choice in a sense in this Feshbach resonance. And this is an opportunity, but it's also a challenge in the sense that it's difficult to characterize and to know what are the properties of the few body physics occurring here. So this is interesting physics in itself, but it will not be, I will not talk more about this now. What I want to focus instead is to go back to this competition of interaction and look at it at a many-body level. And so I have this many-body gas of cloud of atoms, and I want to present to you the consequence of this competition of interaction and the tunability that we have. And this, it's a twofold consequence that is related to the occurrence of quantum stabilization in a system that should be mean field unstable, and the possibility to have a self-organization with a tunable strength of this self-organization. And I want after to show you how this leads to a new state of matter. So this will start my part on this review of the work that we did in particular in Innsbruck, but also of the field. And I want to start with this quantum stabilization, in fact, beyond the mean field instability. So just as a reminder here, like we can have in our ultracold quantum gases a system that is stable, so Bose-Einstein condensate, BC, of finite density if we have mean field repulsion between the atoms. However, if we tune the interaction to be mean field attractive, what occurs normally is that we don't have a finite density state anymore, and in the dynamics, what we see is a fast implosion and explosion that was coined Bose nova, and that result from this, let's say, mean field instability. This was also observed in dipolar gases, in these weakly dipolar gases that are chromium. And the breakthrough in our field came from an experiment that was done in the group of Tillman-4 in 2016, and in which they tried to reproduce this experiment, but now working with dysprosium. And what they observed is that instead of this really fast dynamics and this Bose nova effect, the gas was remaining, let's say, long-lived, relatively long-lived, and forming relatively stable structures that were called droplets at that time. And that was remaining for several hundreds of milliseconds in the gas. So at the time of this experiment, actually, it was not understood what was the effect that could lead to this stabilization beyond the mean field instability. And it's the result of several theory and experimental work that show that, in fact, this stabilization result from a relatively universal mechanism and relate to quantum fluctuations effect. So here I would like to illustrate to you like the main idea of this mechanism and let's say how it occurs in these gases. So the point is that here we have a mean field instability by tuning close to a mean field mean energy, which is 0, by actually competing two kinds of interaction that have different origin, the contact and the dipolar. And these two interactions by themselves, they are relatively strong, but in average, we average to 0. And this means that the gas, even if it's not interacting at the mean field, is still interacting in itself. And in particular, there are interaction of the many-body state involving the fluctuating part of the field in a sense. And the nice thing also in our settings is that we can treat with this interaction in a perturbative manner. And this would lead to this Li-Wang-Yang correction, what we call Li-Wang-Yang, and result like was first predicted by this three person, Li-Wang and Yang, and for the dipolar case by Lima and Pelster. And the interesting part in this formula here, given this Li-Wang-Yang correction, is that it is actually always a repulsive potential for the gas, and it's scaled much like with a larger power of the density. Therefore, what occurs if we tune the mean field interaction to be weakly attractive, the gas will tend to first increase its density, and at some point, this term will become dominant compared to the mean field effects. So that's let's say the basic idea of this mechanism related to quantum effect, to quantum fluctuations. And this was leading to this discovery of a new, let's say, kind of ultra-dilute liquid, which was called a droplet. And it was observed like as a single macro droplet in different experiments afterwards. So this was the first part about the quantum stabilization. Now I would like to go towards the possibility of self-organization and to link it to the concept of elementary excitation and of dispersion relation. So this picture is maybe a bit too schematic for this community, but I just want to illustrate that this concept of elementary excitation that occur on top of a many Bose system, somehow characterized by the dispersion relation, give somehow like the relation between like a certain excitation at a let's say at a certain spatial modulation and let's say the speed of the propagation of this excitation. And this is included in this dispersion relation. And actually this concept of dispersion relation was introduced a long time ago to somehow describe like the really exotic property that were found in superfluid liquid helium. So it was introduced by Landor. And the interesting point also in this early prediction is that Landor identified two kind of excitation of low energy that are important for the property of liquid helium, which has this phonon at low momentum, and also this minimum at a finite momentum, which he called the rotons, and that was later understood as a tendency of the system to crystallize at this like inverse momentum. So now the question is, going back to our quantum gases, how can we understand what are the elementary excitation, and can we also have roton that will somehow correspond to a tendency to crystallize? So the interesting thing in our system is that, again, we can treat things perturbatively, and we can write this dispersion relation via this Vogel-Huber formula that includes kinetic terms and the interaction effect via this, let's say, effective interaction in momentum space. And now, if we look at the contact gases, where we have an interaction in real space, which is a delta function, what we found in momentum space is just a constant, and therefore what we have due to this Vogel-Huber dispersion is simply dispersion relation which includes phonons and directly connect to quasi-particle without any rotons. So there were the question, like following this idea of having, let's say, a spontaneous tendency to crystallize, if we could recover some sort of a roton in these ultracold gases. And this can come if we have dependence in momentum in this interaction. So this may call for like anisotropic and long-range interactions, so in particular to dipolar interactions. So now if we look at the case of dipolar gases and we impose no further confinement, what we found for the momentum-dependent interaction is actually something that is not depending on the norm of the momentum, but only on the angle of excitation compared to the dipole orientation. So we have an anisotropy in the dispersion relation, but again, only phonon and quasi-particle. So then, let's say this is not a roton anymore, again, but there is a way to recover a roton, and this is by applying an anisotropic confinement to our gas. So now having in particular a tight confinement along the dipoles, such that now in the effective momentum-dependent interaction, we introduce this momentum dependence, and in the case of this strong confinement, we can recover a roton. So to just give you an idea of let's say the physical picture in this setting, so I should say that we look now at the excitation in the transverse direction compared to the dipole, so not in this direction of a strong confinement, but transversely. And to give a, let's say, a pictorial idea of what occurs here is if we consider this small momenta, so long wavelength excitation, the density pattern that correspond to the excitation are rather elongated and still, let's say, dominated by head to tail, by side-by-side configuration of the dipoles, so that the main contribution in these density patterns of the dipolar interaction is mostly repulsive. While in the case where the wavelength of the excitation become on the order of this transverse wavelength here, then let's say the shape of this density pattern change and become more and more elongated in the direction of the dipole. So the head-to-tail configuration become important, and therefore we recover, or we find an attractive contribution from the dipole. So this gives rise to this momentum dependence induced by this confinement, and in particular to the roton minimum here, due to the competition again with the kinetic part. So this was like to give a short intuition of this effect that gives rise to the roton in a confined dipolar gases, and to give you a taste also of what is specific in our experiment is that this term here is actually not only the dipolar term in our case, but as I said at the beginning, the sum of this contact part and the dipolar part. And this gives a really nice tunability in our system that we can really control the value of the roton gap by not changing the value of the scattering length via this Feshbach resonance. And we can therefore really tune like the emergence of this roton to its full softening, or even to have it becoming imaginary. So this has been done been observed also in experiment, actually in two sets of experiments that we did in Innsbruck, where we probe on the one side via Bragg spectroscopy on a stable BEC, the emergence of this minimum. So we look at the response of the system by, let's say, imposing perturbation at a given momentum and transferring a certain energy. And we find this white point where we see indeed the emergence of the minimum here. And before that, we actually did another set of experiments that were more related to dynamics. So we were performing an interaction range to a final value of the scattering length that we decreased. And when we decreased this final value, we saw in the short time dynamic the emergence. Now we are looking at the gas in momentum space of these two side momentum peak, which we interpreted as the coherent population of the roton mode. So here in this picture, this axis corresponds to the long axis of the gas. So this is really a modulation at the finite momentum in this long direction. So this was the two observations of the roton mode. And now what we can ask is if we have this possibility to have this roton mode and the ability of also, let's say, fully softening in a controlled way. And we combine this with the quantum stabilization effect that I showed you at the beginning. What happens? Can we find a new ground state? And in particular, can we find a supersolid? So to give you just a short introduction into this concept of supersolid, this supersolid is, let's say, it has been a really debated state of matter that would combine the property of a solid, so with the particle having the tendency to be localized at a certain position of space, and of a superfluid, where the particle will have the tendency to be fully delocalized over the full system and be able to flow without any friction on this full system. So this was debated like from the middle of the 50s with like first Penrose and Onsager saying that it's not possible to have such a state. And after several work, let's say, giving different proposition to observe such a state. There have been also a long experimental quest, as you may know, first let's say, based on solid helium. And there were some claims that this was observed in 2004, but it was later retracted in 2012. And actually, with the advent of ultracold gases, there have been a new direction coming in, starting in particular since 2010, with, let's say, a different direction in which we can find these supersolids, where we would, instead of starting from a solid, now start from a state that is superfluid and try to have this spontaneous density modulation. So there were first systems where this signature of supersolid were found experimentally in 2017. And here I would like just to focus on the case of dipolar quantum gases and the observation that have been done since 2019. So before going to the experiment, we can wonder what we can expect from the theory. And because our system is still quite well described by mean field description, just extended by this Li-Wang-Yang term that I introduced to you, we can compute in this extended mean field description what is the ground state. And we did this in our group in Innsbruck, but it was done also in other works. And we find this phase diagram as a function of the atom number in our system and the scattering length in still this kind of geometry. And what we found are different phases represented by the color, and they correspond to different phases that you have already seen previously in my talk. In particular, in gray here is the regular BC. In these two blue, you have like the different droplets configuration, either a single droplet or array of isolating droplets. And what is now really interesting is this red region, which is quite narrow in scattering length. But to tell you what represents this color scale, this corresponds to like trying to identify in the ground state density structure individual droplets and computing, let's say, the overlap integral between this neighboring droplet, which will correspond to somehow a possibility of tunneling for the atom from one droplet to the other, and therefore to a supersolid phase. So this, in the theory, would identify the supersolid phase, which is, as I said, now in scattering length range. And now I would like to go to the experimental observation, and first to describe you how we would probe it. So in our system, we start from a system that is trapped, and what we can do is to remove this trap and let the system expand. And in the case where we do this on a regular BC, what we find is regular time-of-flight images without any structures. Now, if we start from density modulated state, either this insulating droplet array or a system that would be supersolid and have a global phase coherence, we would find in both cases density pattern, but with different properties. So in the case where we have random phases between these droplets, the interference between these different droplets will lead to patterns, but they will have always different structure in a random way. And if we average over a large set of pictures, what we find is that this pattern disappear in average. On the contrary, if we start with a system that is globally phase coherent and we do this time-of-flight expansion, because the phase relation is fixed between the droplets, we will always find the same pattern in the interference picture, and therefore it will also remain in the average. So to characterize these three different states here, we introduce two amplitudes, which we call AM, to characterize the fact that the individual time-of-flight images are modulated. So this will be a modulated state. And Fi, which will represent the structure in the average picture, so a phase coherent modulated state. So we look at this observable in experiments while we were starting from a gas that was in the superfluid state and slowly ramping to a final scattering length and holding for relatively long time. And these are the amplitude that you observe as a function of the value of the magnetic field, so of the scattering length that we have in our system. And we could observe these three different behavior. First, at large scattering length, we will see no amplitude at all, so no structure in the images. This will correspond to the BC. At some point, this amplitude, these two amplitude AM and Fi will appear simultaneously. This will represent a system that is phase coherent and density modulated, so a supersolid, while after 1.5 and not, or even a bit less, we see that Fi disappears and the density modulation remains. So this will correspond to insulating droplet array. So this was the first observation. It was done also at the same time in different experiments. in the group of Tin Manfo and Giovanni Motuino in particular. In Innsbruck, what we could also do is create this kind of state, not only by starting from a superfluid and creating the supersolid by changing the scattering length, but by a direct evaporation, where we were starting from a thermal gas and reaching the final scattering, the final temperature by changing the depth of our trap. So we could do this at two different magnetic fields, as represented here. And in this value of the magnetic field, we see the appearance of these side peaks that are, let's say, a signature of this supersolid behavior, while in the case of a larger magnetic field, we were not seeing any structure and we were forming a BC. So at this time, this signature are not so, let's say, so good, but because we had the Heidelberg imaging, but we also improved the imaging further and could also observe this state in situ. And based on this new imaging, we could also further probe the evaporation to the supersolids in a second paper here. And in particular, what we were interested is to look into this evaporation ramp to the supersolid and ask what happens first between, let's say, superfluidity and or solidity. So we were looking inside this ramp, and we were again looking at our two amplitude. And what we could see is that this amplitude for the modulation were always appearing before the amplitude for the global phase coherence. So in this sense, in our settings, we were always finding that modulation was appearing before this global phase coherence. In this experiment, what we could also do is to look more in detail into the modulation strength along the lifetime of our supersolid state from its creation during the evaporation run to, let's say, its decay via losses. And what we found when we compare the strength of this modulation for different temperatures that occur during this evolution is that for the case where the supersolid was hotter, we found a larger strength of the modulation than when it was colder. So in a sense, this supersolid state is, let's say, more modulated in presence of larger temperatures, which is somehow a counterintuitive behavior. And I want to highlight that this has been also, let's say, explained in theory by a new paper that has just appeared. So there have been also many follow-up work. I don't want to enter now in the detail, so I think I am already quite late. But so the main direction where people have been looking at is towards proving like the excitation and the dynamical property of this system, in particular, looking at the different branch of excitation and the possibility to have two phonon branch in this system, as well as looking at the direct proof of the superfluidity via the response to weak perturbation and rotations. There are also a search for more complex structures and more toward 2D crystal structures, and also toward a better understanding of these phase transitions. So this will finish my part on this review of what have been done in the recent years and dipolar quantum gases, and in particular in the group in Innsbruck. And with this, I would like to thank also the two teams that have really contributed a lot to this work during the time I was here. And in particular, also Francesca Fernaino, the group leader, and our theory collaborators. So this will be the end of this first and main part. I would just like now, if I can, present for a few minutes the physics that I would like to explore in the new experiment that I've been developing in Heidelberg, and also its experimental status to date. So here, what I would like to study actually is to focus again, so to study again dipolar quantum gases, but not to focus on 2D settings, and also the ability to have, let's say, a versatile trap geometry in the plane. And what I want to have is a full control on this trap shape and on, let's say, the interaction, so both the dipole direction and the scattering length value. And I would like to just introduce some aspect of the physics that I am interested in. And I think what would fit good to this community here is to, let's say, link this physics to actually the new interesting aspect that occur in the physics of vortices in dipolar gases. And this is just a pictorial illustration of a part of this new physics that appear among vortices. And in particular, due to the depletion in density induced by the vortex, we can see this vortex as anti-dipole. And these vortices, they will have new property both, let's say, as a single vortex due to anisotropic effect, but also due to this dipolar interaction between vortices in the stability of the pairs and in their dynamics. And this connects in two different kind of physics that I am interested in. As a first part, I would be interested in studying the, let's say, the equilibrium phase and the phase transition, and in particular, the new features that are expected in 2 dimensions. And where come the vortices is in particular in this, let's say, exotic mechanism that lead to the phase transition in 2 dimensions, but like to a quasi-order state in 2 dimensions, which is the Beresisky-Kostalitz-Foles mechanism. And this mechanism occurs due to the energetic of these vortices in the superfluid case. And because we have this competition between entropy and energy of the vortices, we can have the appearance of an order state via the binding of these vortices in pair of vortex-anti-vortex, where, let's say, the effect on the phase of these pairs are at long distance disappearing. And the physics behind this is related to interaction and also depends actually on the interaction range. And what we could wonder here is what is the role of this interaction between the vortices of dipolar characters? Will it break the Beresisky-Kostalitz-Foles mechanism or not? And if, in any case, what is the role of this anisotropy and of the interaction competition in this physics? The third point now is related to what I presented to you before, and the spatial ordering that occur in dipolar system, in particular the supersolid or the droplet crystal. And the first question is actually, do they exist in quasi-2D settings due to, let's say, the possibility or not of this quantum stabilization effect and of the Lavoisian, related to the Lavoisian term that I introduced to you before. And in this case, what are the transition mechanisms that lead to these new orders? And are they also of VKT type or not? The second part is actually more related now to dynamics. And here, looking at far from equilibrium dynamics or turbulence, in some regime, this is also related to, let's say, it's also driven by vortices and their dynamics and their interplay with other waves. And here again, we can wonder what is the role of the dipolar interaction between the vortices, the role of the anisotropy in this interaction, and also even to the interplay with other kind of waves like the rotons. So this is what we want to do. We are not at the stage where we can do all this, but I would like to also show you a bit our status. So this is the picture of the lab when I arrived actually in Heidelberg, and this was roughly 1 year ago actually, and where we had the first setup mounted, and these are the people that contributed to the development of this first setup. The specificity, here we can see the setup also more than 1 year ago and like a month ago, roughly, and we saw the development of the optics in the two cases. And to describe quickly our setup, so we work with dysprosium, but we develop a novel scoring scheme that rely, let's say, on a new way to create a beam of slow atom to load the 3D modes. So there are some benefit in this scheme. I will not enter in the technical detail here, but there are also some challenges. And for this reason, we were quite happy that it worked in experiment. And I will just flash like what happened over the last year. So in April last year, we had our first source in the sense of these slow atoms that you see here. 1 month after, we could load our first 3D mods, and we actually also published our first paper 2 months ago on the archive on this new source. So if you are interested, you can have a look here. Then we could load an optical dipole trap from this three-dimensional mod. And we could also achieve a bit more than 1 month ago our first Bose-Einstein condensate, and we could optimize it, and also we are characterizing it and trying to understand how to tune all the parameters. So based on this, the next step are like to do maybe a first measurement on this 3D quantum gas, and then to get some further improvement in our setup related to reaching dense two-dimensional settings with high resolution imaging and also tailorable in-trap shells. So this, I would like to thank you for your attention, and also thank the new team that is working in the lab right now. And I am happy to take your questions.
Thank you, Lauriane. Very exciting talk and great overview also of the theory and experiments of dipolar gases and BEC. So I think that there is already a question by Luca. So please do unmute yourself and ask the question, please.
First of all, thanks a lot for the nice talk. My question is, when you are observing the modulation of the density in the supersolid phase, can you relate this density modulation to the superfluid fraction of the system, for instance, by using the zero temperature Leggett formula?
So in theory, you can relate, yes, this density modulation to the superfluid fraction. We have this formula, indeed. Okay, the question is how to do this connection really in experiment. There have been actually experimental results that maybe you know in the group. Okay, in the group of Jean Dalibard and Jérôme Pognon, and also, no, I don't remember, but another experiment did also this, where they study this connection in optical lattice, like in a superfluid in optical lattice, and they could make the connection to some rules.
Okay, thanks a lot.
But this has not been done, this connection, direct connection has not been done in experiments with supersolids.
Okay, thanks a lot.
Any further question for Lauriane? Maybe in the meanwhile, I can ask a question. So in one of your last slides, I think on the first part, if I remember correctly, you show the two branches in the dispersion relation.
Yes.
So can you explain why there are two branches? I missed that point. Sorry.
Yeah.
Thank you.
I can try. I want to go back to this slide, but I don't manage right now. So because I have a laser pointer, but So to start answering, the point is in the supersolids, you are breaking two symmetries at the same time, spontaneously, let's say, the phase and the translation symmetry. And through the Goldstone theorem, you would expect that each breaking of the symmetry lead to a gapless phonon branch. And this is like the underlying idea of this of these two branches. And actually, okay, it's here. And actually, the modes that are in these two branches, they have different character. They can be more related to, let's say, an oscillation in population, and this will relate to the phase, or it relates to really let's say, a modulation of the position of the droplets in the crystal, and this would relate to the translation symmetry.
Right.
Okay. Yeah.
Thank you. Thank you. Really interesting. I think Anton has a question.
Yeah, let me try to it not seems to turn on my camera. Question, when you looked at the transition between the isolated droplets and the supersolid, have you ever seen an intermediate phase, and if yes, how big the region was, where the phase of the isolated droplets, as I understand, they are kind of random, and when you go into the supersolid, the phase is the same across the condensate? Have you ever seen a intermediate state where the phase is kind of depends on the position inside the condensate? It's not uniform yet, but it's correlated. Thank you. So
you think you would say, like, if we have an array of droplets, but some of the droplets are correlated, but not all. Is what you mean?
Something like that, yeah, where the phase of the condensate is spatially dependent.
Yeah. Like in experiment, we haven't seen any signature of this. And I should say that for now, like in this system that have been explored in experiment, the size of the crystal are still relatively limited. So it will be difficult to really see something in between, I think. Like you can see in this picture that is on the side here, there are something like 7 droplets. And also in the case of the linear chain, it was roughly this size of system or even smaller that were observed. But yeah, in theory, I don't know if you expect an intermediate phase or at least an intermediate behavior. It's not really clear even what is the, let's say, the transition, the order of the transition, or if it's a transition or crossover, what occur in between these two states.
Thank you.
We also have a question in the chat from Srivatsa. Sorry, maybe I've not pronounced it well. So they say, I might have missed this, but to the best of your knowledge, have there been experimental theory studies of periodic driving of the scattering length across the superfluid supersolid transition?
A periodic driving? I think yes. Not. I think there were no. I don't know any experiment, and I don't know any theory on this. There have been quench experiments, but not periodic driving.
Okay, thank you. We have a question by Robert.
Yeah, thanks, Lauriane. Thanks for the nice talk. My question is about the what you showed about sort of cooling into the supersolid state. And I'm just wondering, yeah, how much do you think this is sort of equilibrium physics and non-equilibrium physics?
Yeah, I think it's difficult to say. I think it was not fully equilibrium because the ramp they were relatively fast, and it's not fully, let's say, yeah, I would not say that it's fully thermalized. And okay, you can see also actually in this graph, if you look, the temperature is still evolving during the time that we are holding after the ramp. So in this sense, there are still, yeah, some dynamics going on, just also from the thermal part.
Great, thank you.
And we also have a question from Nicholas.
Yes. Hi, thank you for the talk. Is it possible, I was wondering if it is possible to control the size of the droplets and also the mean distance between the droplets? Is that possible to do?
So yes, maybe there's something I did not highlight so much, but one thing that sets the size of these droplets, or at least the size of the roton excitation at the full softening, is the size of the clouds of the trap in the transverse direction. So if you would make this, let's say, smaller, you would also reduce the size of the droplet. It's not clear to which point you can do this.
Okay, and compared to the size of a quantum vortex, is it comparable or?
Okay, for a quantum vortex in a supersolid, you mean?
Yes, yeah, that kind of.
So there have been theory work on this. What is the size of the vortex in a supersolid and where does it go actually? It seems that it's mostly going in between the droplets, and in this sense it's quite big because the density is small. And it's roughly the same size, yes.
Okay, thank you.
Might have a question which is related to the confinement. So when you confine, is it really like a strong 1D or 2D? So there are no motion.
Yeah, no, in this case, like of all this experiment, it was very 3D. It was just elongated in a cigar or in a backhand shape, but the confinement was really weak in the transverse direction, something like 150 Hertz. And so, yeah.
So that means that you still have a lot of degree of freedom in the
Yes.
confinement. I see. Okay. Thank you.
And the density are not too high also.
Okay, thank you. Any further question for Lauriane? Well, if not, well, let's just thank Lauriane again for this really nice talk.